Okay, so in your file is going to look like this. Okay, again, you're filling in. That's the template built for you. You need to fill everything in as we go here. Okay, I will go through explanations. So the problem we're investigating here has to do with when and why chemical reactions occur. Right? So when substances are mixed, their chemical properties, not their physical properties, their chemical properties determine whether a reaction will occur. What evidence do we have that a reaction takes place when substances are mixed? Okay, that is kind of the key part of the problem. We are trying to determine what the signs of a chemical reaction are. All right, so you need to rephrase that in your own words as a question for your problem. Okay. Now, for your design and variables. Okay. The lab is going to go like this. I'm going to have these pairs that you can see down here in the procedure. All right. You are going to mix the different pairs of materials. So when it says pair 1 is A and B, that means you're going to be mixing sodium hydroxide with ammonium chloride. All right. So you'll be mixing those two things together. Everybody follow so far? Yes. Okay, so those are the things you'll be mixing together in pair 1. Then in pair 2, you'll be mixing different things together. Pair 3, different things again. Pair 4, and so on and so on. Okay, every time we do this, we're mixing a different combination of, what do we call those things that start a reaction? Reactants. All right, so every time is a different pair of reactants that the experimenter is using. Don't see a lot of people typing that, but I've kind of just given you a big juicy hint for one of them. All right. In terms of what we're watching for here is, okay, when we mix things together, we want to see what happens. Now, we don't want to write it that way, obviously, okay, but we want to look for changes. Right? Every time we mix something, there should hopefully be some change, okay, or some sign that a chemical reaction has occurred. Right, so we're going to be looking for those signs we talked about the other day, color change, temperature change, odor, bubbles, okay, all that kind of stuff. We're going to be looking for those signs, okay, maybe a precipitate forming, that kind of stuff, right? Every time we mix something, we're going to be looking for some sign that a chemical reaction has occurred. Now, things that we need to make sure of while we're running the experiment, all right? What kind of things can affect how quickly a reaction happens? Agitation, heat, so temperature, surface area, okay, all of these kinds of things. So I want you to think about those things. If we're trying to honestly compare different reactions, all right, and different, mixing different things together, we should probably be cautionary about those types of things. Anything that could affect how a reaction occurs would need to be controlled in the lab. Many of those variables are environmental. Okay, so we're not actively controlling them so much as we are just going into an area where they are going to remain the same. Okay, so you need to think of 3 controlled variables that could affect how a reaction occurs, okay, and explain how you're going to control them and the effect that they would have. Right? Now, for our hypothesis, a little bit trickier on this one. Okay, again, the if part needs to talk about the premise here. Okay, the premise that we're working on is that reactions occur because of chemical properties. That's the premise we're working on. So the if part of our hypothesis should probably talk about that. I shouldn't say how. It's not how. If. Okay, so you need to talk about something to do with chemical properties and reactions. Okay, that's what needs to be in the if part. Okay, the and part is going to describe the experiment as always. Okay, we're using different combinations of reactants and, watching for signs of a chemical reaction. Okay, in the then part, this is going to be the longest part of the hypothesis. Okay, I want you to not only kind of identify what signs might occur, but why they might occur. Okay, and what I mean by that is when a reaction has occurred, we see things like color change, bubbles, all that kind of precipitates, whatever. Okay, why do we see that after the reaction? Okay, and it has something to do with this. Okay, so we want to talk about signs of a chemical change. Okay, and that those occur because of this idea here. So it'd be like, then the following signs will be observed because talk about new substances and physical properties. Okay, so after that, we've got some initiating and planning stuff we need to go through. First says read the procedure before starting the lab. We've kind of talked about that already. Okay, review the indicators of a chemical change. We've done that. Okay, create a system or chart for recording your observations throughout the lab. I believe I put one in here, did I not? Yeah, okay. So you got observations here. My suggestion is this. This may need to be split in half, so you have a before and an after. Okay, you need to probably describe the reactants had this appearance, the products have this appearance, okay, so that we can, clearly show that signs of a chemical change occurred. All right, so I would suggest that when you're building this chart, it should have a before and an after section. Now, the other thing we have to do as part of our planning is we need to predict these reactions. We're not going to be right on all of them, and that's fine. Okay, but this is how I'm going to introduce predicting reactions to you. All right, so you're getting a bit of a freebie here. Okay, I'm not going to balance these reactions, but you're going to need to do that. But I'm going to help you predict them. Okay, and as I said before, we're going to predict some of them wrong. Okay, that's just the way it's going to go. Okay, but we'll fix that when we talk about the analysis tomorrow. Okay, so let's go back to here. Okay, so the setup of the lab, guys, is going to be like this. Again, I'll have all the reactants up front. Some of them are solutions. They'll be in the Erlenmeyer flasks. Okay, some of them are solids, so they'll be in the beakers with a scoop. Okay, again, make sure you do not take the eyedropper or scoop from one and use it in another. I don't want the reaction taking place in my samples. Kind of an inconvenience. Okay, so make sure it stays in the place you got it from. If you forget where you got it from, then come up and say, Mr. Coderre, I don't remember where this came from. Throw it away, and I will get a replacement. Okay, it's not that big a deal. Eyedroppers are cheap, solutions are not. Okay, everybody with me there? Okay, we are addressing one major source of error we had in the first lab, sample size. So instead of doing all of these reactions in that tiny little depression plate, you are now going to get this big giant watch glass. It's a piece, it looks like a contact lens, but it's about this big. All right, so you are going to perform the reactions in there. So it's a little dish. You have to be careful because it wobbles, okay? But you're going to perform the reaction in that dish, one at a time. All right, so you'll have much better sample size, much better ability to observe what happens. Okay, that's the waste bucket. Everything goes in the waste bucket. Nothing goes down the sink. Okay, everything has to go in the waste bucket. We have to take it to the fire station, and they usually send it to like Swan Hills for toxic disposal. Yeah, because if that stuff goes into the sewage system, it'll end up in the river, and we'll have three-eyed fish like on The Simpsons. So we don't want that. All right. So here's what we got to do. We've got to predict these reactions. I keep grabbing the wrong color. Okay. Yeah. 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 Something like that. Well, there was the one that had a lot, but there was the first one had 3. Yeah. And it was the squirrel that had like 50. Yeah. Right. Okay. So we've got here, guys, a reaction that starts out with sodium hydroxide reacting with ammonium chloride. Okay. The first step in predicting a chemical reaction is to identify what type of reaction is occurring. What type of reaction do we know of that starts with 2 ionic compounds? Nope, that starts out with 2 elements. Double replacement. Okay, a double replacement reaction starts out with 2 ionic compounds. And what we do in a double replacement reaction is we swap the things that are acting as metals. Sodium is a metal, and ammonium is a positively charged polyatomic ion. It also acts as a metal. Okay, so on this side, okay, sodium is going to have a new partner, and ammonium is going to have a new partner. Okay, who is sodium going to end up with on the product side? Chloride, right? Okay, and ammonium is going to end up with hydroxide. Okay, so we've just predicted that reaction. Right? Wasn't hard. All we had to do is identify the type of reaction that was happening and know what happens in that reaction. That's easy to figure out who goes with who. Okay, now that's the way we've predicted it. In the lab, it may or may not work out that way. Okay, but that reaction, if it happens that way, okay, who knows what the signs of that might be? Okay, maybe one of the, well, sodium chloride is soluble. Ammonium hydroxide is also soluble in water. So I'm not sure what the signs of that reaction would be, but we would have to watch for it. Okay, maybe it doesn't go as we predict, and maybe something else occurs, and we'll have to change the reaction. That's fine. We'll deal with that when we get there. All right, this one here is also a double replacement reaction. This is an ionic compound, even though it's not written that way. Okay, it really should be written this way: HCH3COO, but for some reason it's not. Okay, so this would be that's the proper way to write it. I'm just showing you so that we can do the replacement. Okay, so hydrogen is acting as the metal, even though it's listed over here in this compound. Okay, so this is what we call acetic acid or hydrogen acetate. Okay, commonly known as, some people put it on fries, vinegar. Okay, and it is reacting with sodium hydrogen carbonate, also known as baking soda. Okay, so this is vinegar and baking soda, except I'm using lab grade. So it's not the vinegar you buy in the store that's 5% acetic acid. This is like 80. It's glacial. Don't get it on you. It'll burn a hole in you. Don't put it on your fries. It'll eat them for you. Okay? Don't do it. All right. So in this reaction then, hydrogen is acting as the metal, acetate the non-metal. Okay, it's a negative one. Okay, and then we have sodium with hydrogen carbonate. So this is the plus and that's the minus one, the hydrogen carbonate. Okay, so on this side, who is hydrogen going to end up with? HCO3. Okay, so we're going to have like then H2CO3. Okay, something like that. Okay, plus, and then we'll have sodium will end up with acetate. Okay, so we'll have sodium acetate. Okay. Incidentally, sodium acetate is an ionic compound. It is a crystalline solid at room temperature, and it is often used to flavor things. It's the vinegar flavored salt that they use on things like salt and vinegar chips, okay? Because it has acetate in it, it tastes like vinegar. But you don't have the problem of soaking a bag of chips in vinegar and then putting them on the shelves, because then they're kind of soggy. Okay? This keeps them crunchy. All right, pair number 3. What kind of reaction is that going to be? Also a double replacement. Okay, so who is going to be sodium's partner on this side? Chloride. Okay, who's magnesium's partner going to be? What do we call this stuff? Hydroxide. Okay, now here's something we haven't done because we haven't had to yet, but This is a +2, and that's a -1. What do I need to do with this? All right, I got to drop and swap. Okay, so I got to make sure I'm checking all of that stuff. Okay, and making sure that my ionic compounds are correctly done. Okay, pair 4 and pair 5 we don't have to predict because this is an indicator reaction, and you don't cover those till like Chem 30, but we're doing it just because it has a good sign of a chemical change. All right, so we won't have to do those two. Pair number 6. Okay, I'm going to let you guys try pair 6 and pair 7. Okay, figure out what kind of reaction it is, do the swap. So see if you guys can do the prediction. Remember, I didn't balance any of these. All right, so you may need to go back and check to see if they are balanced. All right, but you guys can predict those, okay, as best you can. And then tomorrow we'll talk about the procedure and analysis and conclusion when we come back from the lab. We will not have the Chromebooks tomorrow though. Okay, they're booked out, so you may have to make some notes on your phone in Google Docs or something like that tomorrow instead. Okay, so I want you guys to see if you can predict the products of these. Okay, so what kind of reaction, I'll help you out here. What kind of reaction is pair 6? Double replacement. What kind of reaction is pair 7? Single replacement. Okay, remember that in a single replacement, the thing that's alone replaces the thing in the compound that's like it. Zinc is a metal. It's reacting with hydrochloric acid. Okay, so the H is acting as a metal. All right, so we'll have you guys finish up, okay, for class today, and then like I say, tomorrow we're in the lab. I guess I better get the samples made. I don't have them ready yet. Okay, so that's what we'll be doing tomorrow. Okay, and remember, guys, appropriate stuff for the lab. Make sure you got good footwear, hair tie if you got long hair. Okay, try not to wear anything that's got drawstrings or is really loose that can get into stuff. Right, we don't want any of those kinds of issues happening tomorrow.